So the discussion of the second law is facilitated by the introduction of a useful concept, and the concept is that of a Carnot engine. Okay. I guess it was French, so you don't pronounce the T. Okay, so Kelvin's statement of the second law doesn't convert some heat to be converted into work, right? All he said that you cannot convert all the heat to work. So you can, maybe there's a way to convert some of the heat to work and let a little bit of it go to waste. And but then the question becomes, how efficient is this conversion, right? So the whole idea of Carnot engine is introduced to discuss that, that quantification. So a Carnot engine is essentially a reversible system which goes through a Carnot cycle. So what's a Carnot cycle? So Carnot cycle. So a Carnot cycle is the following. Suppose that you have an ideal gas in some container. What you do is that you hook it up to some temperature, hot temperature, T of H, which it is at, and you let it expand. Okay, so you let it expand isothermally. So you keep the temperature constant and you let it expand. So that means that it's going to, so this is an isothermal expansion. So, and then once it has expanded, you allow it to keep expanding, but now you isolate it from the environment so that the rest of the expansion happens adiabatically. And once that has happened, what will happen is that it'll decrease the temperature, right? Because you're not keeping the temperature constant anymore. It'll decrease the temperature to some lower value. So then what you do is that you connect that to a reservoir which has that lower temperature, Tc, and you compress the gas isothermally. So this is isothermal expansion, this is isothermal compression. And after a bit, you again isolate it and keep compressing it. Sorry, this picture should be, let me just, you keep compressing it until it reaches its initial value. And you do this adiabatically. And if we were to plot this process on our PV diagram, what we would see is that we start at some point A, and then we do a isotherm, we go down this isotherm to another point B, and then we go down an adiabat. So this is B, and this is C, and then we compress it again isothermally to some point D, which is connected to A through some adiabat. So we take this path. Okay. So this is called a Carnot cycle. And in terms of T and this other constant quantity that we didn't really specify when we did the adiabatic expansion, remember when we were doing the adiabatic expansion, we say P, V, gamma is some constant. So, we could have said, okay, instead of the PV diagram, we could have said this T diagram, and let's call this other quantity S. Then isothermal expansion would be like that, and then adiabatic expansion would be like that, isothermal compression would be like that, and then adiabatic would be like that. So, and from what we saw before, isothermal expansion means that there is heat flowing in, QH.
So
And
wouldn't that be adiabatic compression, the arrow upwards? Or will that be there?
yeah, you're right. Yeah, of course, yes. Yes. Yeah, thank you. So, and here we would have Q cold, right? So the Carnot cycle has 4 parts. The first part, again, I'm just reviewing. The first part is it goes from A to B, and the gas expands at a constant temperature, TH. And because of the expansion, the gas can do mechanical work on its external system. So that's what an engine does. An engine uses thermal energy converted into work energy. And this, and then in the next step, we isolate the gas from the heat reservoir, and it continues to expand, but the temperature, it expands adiabatically, and the temperature falls to some level, and then we connect it to a reservoir at a lower temperature, and then we contract, keeping it at the same temperature. And now it tends to, when we're compressing, it would tend to heat up, but of course, because we're connecting it to a lower temperature, we are keeping its heat constant, its temperature constant, and therefore there'll be heat keep seeping out of the system, which is this heat, and then we adiabatically contract it to the initial position. Okay. Now we can introduce a factor called the efficiency factor for the Carnot engine. And the Carnot engine is that how much work can a Carnot engine do given the amount of heat that was given to it. Okay. Now, since according to the second law, not all the heat can be according to Kelvin, not all the heat can be converted to work. This means that a Carnot engine, the efficiency must be less than 1. Okay. So schematically, we can represent a Carnot engine by a circle. So this is Carnot. Sorry. This is, and this is a reservoir at a high temperature, and this is a reservoir at a cold temperature. And this is, the Carnot engine is reversible, so these guys can go in any direction. It's absorbing the heat QH, and it's giving up heat QC, and it's converting the difference between to work W, okay? Now, in the next class, we will prove Carnot's theorem. And Carnot's theorem tells us that Carnot is the best, okay? That of all the heat engines working between two given temperatures, say TH and TC, Carnot's engine has the highest efficiency, okay? We shall prove this, and we shall prove this using reductio ad absurdum. So we are going to assume the opposite and then show that it violates the second law of thermodynamics. So I think I'm going to end here. And before we take some questions, did I forget anyone to give you an attendance? So did Mahfouz show up? No. Did Wadiha show up? No. All right. Rahul, are you there today? No. Ahmed Zabir Hussein? No. All right. Nusaiba, are you here? No. Zakaria FM? No. Oishik Hassan? No. Okay. All right. So we have a few minutes for questions. Okay. So what I'll do is that I'll post the, usually I make the tutorials the night before the tutorial. So it's not always possible to give it very early, but what I'll try to do is I'll try to make the tutorial tonight so I can give it to you by tomorrow.